Hello and welcome back to Calculus. First, I'd like to thank all the nice people who support this channel by liking and subscribing. Today, I'd like to explore the concept of implicit differentiation. So far, every time we did a derivative, we had a function y expressed explicitly in terms of x. And we differentiated it with respect to x. We call it explicit differentiation since y is expressed explicitly in terms of x. However, there are functions that cannot be explicitly expressed, but rather implicitly. For example, this one. As you can see, here we have a function, however, it is not written as y equals to and everything in terms of x. We have a mix of x and y's, and then it's equal to 0. So how would we compute the derivative of such an implicitly expressed function? And this is where we use the implicit differentiation. First, however, we have an equation here, meaning we have to take the derivative of both sides. Firstly, on the right-hand side, the derivative of 0 will remain 0. On the left-hand side, however, we basically have 3 terms added and subtracted, and this means we can just do the derivative of each term separately. So first, the first term, the derivative of x cubed, is going to be 3x squared, and we get this using the basic power rule. Next up, we have the y cubed term, and I wrote this on the right hand side separately because here we will actually have to use the chain rule on y. But first, we do use the power rule. The derivative here would be equal to 3y squared. But then we also have to differentiate the y itself, the inside. Therefore, by the chain rule, we simply get y prime or y derivative. You can also express this as 3y squared times dy over dx. Remember, y prime and dy dx are the same thing, just expressed differently. Next up, we differentiate the third term, the 9xy. Here, we have a multiplication between two functions, 9x and y. This tells us that we will have to employ the product rule. So, by the product rule, first we have 9 times y, where 9 is the derivative of 9x, and then we add this with our original 9x and times the y derivative. So now that we have all of these terms differentiated separately, we can put it all together into one. This right here is the full expression for our derivative. However, that is not all, because on the left-hand side, we have a mix of everything. But what we want is an expression of the derivative, or in other words, of the y prime. This means here we have to move things around. So first, let's take the terms that do not have y prime and move it from the left-hand side to the right-hand side. Now that we have done this, on the left-hand side again, we can actually factor out the y prime. And then finally, we can just divide this term in the parentheses on both sides so that we can get an expression of the y derivative. And this right here would be the final answer to our derivative. The y prime is expressed as 9y minus 3x squared over 3y squared minus 9x. Note that the answers here can have both y's and x's in them. Okay, so now that we have gotten the theory of implicit differentiation out of the way, I would like to go back a little. Please recall from the last video, I provided an example for the derivative calculation, and the final one had the inverse trig function arcsin in it. I told you immediately at that time that the derivative is 1 over the square root of 1 minus x squared. But I did not explore where it came from. Well, the inverse trig functions, arcsine, arccosine, and arctangent, are actually all closely related to implicit differentiation, and I will show you how right now. So basically, we have a function y equals to arcsine of x, and we are asked to compute its derivative. We can actually first rewrite this function in terms of a normal sign. This basically means sine of y is going to be equal to x. That's the definition of the inverse trig functions. Now, from this step right here, what we do is implicit differentiation. So we implicitly differentiate both sides with respect to x. So on the left-hand side, the derivative of sine is going to be cosine of y. And of course, we do have to apply the chain rule because we're differentiating y. This means on the outside, we get multiplied to y prime or y derivative. And on the right-hand side, the derivative of x is simply 1. Now, if we divide both sides by cosine y to isolate y prime, what we get is 1 over cosine of y. Now, the next step is actually going to be to express cosine y in terms of x. In order to do this, you do need to know the Pythagorean identity. That says that y squared, sine squared of y plus cosine squared of y is equal to 1. So basically, cosine squared of y can be written as 1 minus sine squared of y. And then finally, we just have to take the root of both sides in order to get rid of the square root of the square for cosine. Now we are almost there, because as you can see, here we have the square root of 1 minus sine squared y. However, in the very beginning, we said that sine y is actually equal to x. So basically, cosine of y is going to be equal to 1 minus x squared, the square root of it. So now that we have expressed cosine y in terms of x, we can go back to our derivative of y and write it as 1 over the square root of 1 minus x squared. And this here proves why the derivative of arcsine x is this right here. Now, as a little challenge for you, you can actually try to differentiate y equals to arccosine of x. You can do this using the same method, and in the end, you will also have to apply the Pythagorean identity. In order for you to check your answer, I will immediately tell you that the derivative of arccosine is going to be the same as of arcsines, only with a negative sign in front. And actually, the same thing can be done for y equals to arctangent of x. And I will go through that very quickly right now. Again, using the property of inverse trig, we get x equals to tan y, and next up we'll have to differentiate both sides. Derivative of x, we get 1. Derivative of tangent y is going to be secant squared y, and of course by the chain rule multiplied by the derivative of y. So then, what you have is 1 over secant squared of y equals to y prime. Now here, once again, we will have to do the same thing with the Pythagorean identity. However, here, we will have to use a different one because secant squared of y can actually be written as 1 plus the tangent squared of y. Now, tangent y is just x, meaning secant squared of y can be written as 1 plus x squared. And finally, this tells you that the y derivative or the derivative of the arctan is going to be 1 over 1 plus x squared. Please remember these three derivatives. They are quite important. However, for some of you, they might be given in the formula booklet when you solve a test or solve an exam. For others, it might be different. This video here concludes everything we need to know about derivatives and how to compute derivatives. In the next video, I will go into the application such as kinematics. That basically means speed, velocity, and acceleration and how they are related to differential calculus. So, I hope to see you there and have a nice day. Bye!